Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Maxim Susloparov. Maxim Susloparov earned his bachelor degree in applied mathematics from HEC University in 2020. He currently works as a trainee researcher at the IIT RAS and HEC University. He conducts research in the field of data transmission via 5G cellular systems. Today, he will present us his recent results about AR/VR traffic balancing algorithms for 5G systems. Maxim, the floor is yours.
Thank you, Vyacheslav. Good evening again. My name is Maxim Susloparov. I am a trainee researcher at Institute for Information Transmission Problems and Higher School of Economics University. In today's seminar, I would like to present you my talk titled Study of AR/VR Traffic Balancing Algorithms for 5G Systems. The outline of my talk is as follows. Firstly, I will introduce you to the subject of my talk, which is the transmission of cloud AR/VR traffic with the aid of the multi-connectivity feature present in 5G systems. I'll also define the problem of cloud AR/VR traffic balancing in 5G systems with multiple base stations. Secondly, I will describe existing traffic balancing algorithms along with the algorithm specifically designed to solve the problem mentioned before. Thirdly, I will present the results of performance evaluation of the algorithms and compare them. Finally, I will make conclusions. You can ask me questions in the Zoom chat as I speak, but I would like to answer them after I finish my talk. Let me start with the introduction. Augmented and virtual reality, or AR/VR, are rapidly evolving technologies designed to create a virtual 3D environment around the user. These technologies find many applications, such as gaming and entertainment, industry, medicine, training of driving and aviation skills, and so on. The global AR/VR market value in 2022 exceeds $200 billion and is expected to grow exponentially each year. The state-of-the-art AR/VR headset devices are capable of displaying high-resolution video streams with high frame rate. Such a video stream requires immense computational resources to ensure smooth rendering and post-processing. Instead of buying very expensive hardware nowadays, a user can subscribe to a cloud AR/VR service, which will render the scene on the remote server and send the ready-to-use video stream to the user. In an example of NVIDIA Cloud XR service, a complicated 3D environment of the AR/VR application is processed by a powerful GPU cluster, which then renders the video stream. After this, the NVIDIA server uses one of the wired or wireless technologies, which we will discuss on the next slide, to deliver the video stream to the XR devices. XR stands for extended reality and is a combination of virtual, augmented, and mixed realities. But during this talk, I will use the AR/VR term only. As wireless connection options, like I mentioned on the previous slide, we will consider Wi-Fi and 5G. Wi-Fi is one of the most common ways to connect the AR/VR headset device to a computing server. This approach provides a reliable connection in line of sight and low range scenarios. An example of such a scenario will be a room in an apartment. Because a Wi-Fi network provides local area coverage, the user is noticeably limited in mobility. Another issue is a possible uncontrolled interference caused by other devices and networks. Now let me consider a 5G system for transmitting the video stream. Because the 5G system provides significantly wider coverage, the user may move around by longer distances. Another advantage of a 5G system is that it is designed to serve dozens of users which may receive different types of traffic. This is useful when there's an objective to provide cloud AR/VR service for many users on a large area. And with 5G, it will be easier to organize. As I said before, the AR/VR video stream is rendered in high resolution with a high frame rate. Therefore, there are strict quality of service requirements for its transmission over the internet. For example, for 4K 60 frames per second stream, throughput should be at least 60 megabits per second. Latency should not be more than 15 milliseconds, and packet loss, frame loss, excuse me, should be less than 1%. Violating these requirements will result in poor user experience. The currently dominating cellular system standard, LTE, fails to fulfill these requirements, as according to the reports, average throughput is approximately 50 megabits per second and average latency exceeds 40 milliseconds. 5G base stations, also called G-Node-Bs, operate in two frequency ranges, FR1 with carrier frequency below 6 gigahertz and bandwidth up to 100 megahertz, and FR2, also known as mmWave, with carrier frequency between 24 and 53 gigahertz and bandwidth up to 6.4 gigahertz. Using FR2 allows to massively increase throughput to the order of several gigabits per second. However, the throughput fluctuates widely and in some occasions may drop down to zero due to high attenuation in this frequency range. Therefore, constant usage of FR2 is not viable for transmitting the AR/VR traffic, as severe packet loss may occur. To solve this problem, a user or user equipment can use the multi-connectivity feature. The user connects to several G-Node-Bs at once, where a G-Node-B may operate in either FR1 or FR2. An FR1 G-Node-B allows to send data reliably, whereas FR2 G-Node-B boosts throughput when channel conditions are favorable. G-Node-Bs are also able to exchange data by using the XN interface. Let me define two terms. A master G-Node-B or mG-Node-B is a base station typically operating in FR1, which serves as a coordinating base station, which defines the multi-connectivity logic. And secondary G-Node-B, or sG-Node-B, operates in FR1 and might receive user data from mG-Node-B for transmission via FR2 channel. I will use these terms in further slides. Although multi-connectivity is documented in the 5G standards, they do not clarify how to distribute the data among the base stations. It is up to hardware vendors to implement the algorithm which balances the traffic. In the case of cloud AR/VR traffic, strict QoS requirements should be met, and FR1 channel resources should be used sparingly because the FR1 channel has a narrower bandwidth in comparison to FR2. And this bandwidth is also used by more connected devices. Now I will describe the traffic balancing algorithms I just mentioned. I will discuss existing algorithms typically designed for eMBB traffic or saturated traffic. They have been either introduced in the official 5G standards or proposed in literature. I'll also talk about the newly developed delay-based traffic balancing algorithm, or DBTB, which was specifically developed for cloud AR/VR traffic transmission. Link switching, also called handover, is an algorithm where the mmGNOT-B periodically gathers channel state information and selects one GNOT-B, not excluding itself, for data transmission for the current time. The GNOT-B can be selected following common metrics, such as signal to interference and noise ratio, or SINR, or estimated throughput, which also accounts for channel bandwidth. This method allows to reduce FR1 resource consumption, but introduces packet loss caused by FR2 channel becoming unavailable during the transition to the FR2 channel. It might be fixed by increasing the period of channel state information update, but it will in turn increase both computational load at the GNOT-B and the load of the external interface. Moreover, the user equipment's packet data convergence protocol will have to reorder way more packets, which will cause additional buffering at this layer and increase latency. Packet duplication constantly sends the data via both GNOT-Bs, and user equipment's packet data conversions protocol removes the duplicates and properly reorders the packets. Although reliability increases because of constant data transmission via both channels, the FR1 resource usage rises to the maximum because it is used all the time. The packet splitting algorithm divides the incoming data into portions, which for cloud AR/VR traffic conveniently correspond to video frames. And each video frame is split into two parts, which are forwarded into corresponding GNOT-Bs for further transmission. The way to split the video frames and minimize the delay is splitting this portion of data in the proportion of throughput of the corresponding GNOT-Bs. This algorithm achieves low latency and balanced load between the GNOT-Bs. However, this algorithm does not provide high reliability for the cloud AR/VR traffic for exactly the same reason that link switching algorithm does not as well. If we send a part of a frame into the FR2 channel and right after that it becomes unavailable, the whole video frame becomes invalid and gets discarded. To solve the problems outlined before, we have designed an algorithm called delay-based traffic balancing, or DBTB. The main idea of this algorithm is as follows. We have to transmit the data constantly with almost no packet loss. We also do not want to use the FR1 channel too much. So initially, mmGNOT-B just tries to redirect the data to sGNOT-B only and wait for acknowledgements. mmGNOT-B buffers the same data and keeps track of the expected delivery time via mmGNOT-B. So the packets are not buffered for too long for them to be delivered to the user equipment. If a packet's expected delivery time exceeds the delay budget, it gets transmitted by mmGNOT-B. With this approach, mmGNOT-B is used only when there is no possibility to transmit data via SG0B. And as mG0B prevents the packets from buffering for too long, the video frame latency does not exceed frame time. Here I will describe the DBTB algorithm in more detail. mG0B receives a packet, creates a duplicate for it, and sends it to SG0B for transmission. The same packet gets enqueued to a dedicated queue, and this queue is individual for each data flow. It gets assigned a timer dependent on the delay budget and the time needed to transmit the packet via the FR1 channel. Later on, if SG0B sends an acknowledgement for a packet of this queue, it gets removed from the queue. If SG0B does not send an acknowledgement and the timer of the head packet expires, it gets dequeued and sent via mG0B. In this section, I will present the results of performance evaluation for the traffic balancing algorithms I introduced. The scenario we use is dense urban macro, for which the physical channel model is provided by 3GPP. Several stationary users are randomly placed inside of a hexagonal cell and request for AR/VR traffic. The G0Bs, namely mG0Bs and SG0B as defined earlier, are placed in one of the cell's vertices. The diagonal of the cell is set as 133 meters. We use a network simulator called NS3, and the simulation parameters for it are listed on the slide. Let me mention several key settings on the table. The mG0B's carrier frequency is 3.6 gigahertz and bandwidth is 100 megahertz. And the SG0B's carrier frequency is 28 gigahertz and bandwidth is 1 gigahertz. The AR/VR video stream's average bitrate is 50 megabit per second, and the frame rate is constant 60 frames per second. The peak to average frame size coefficient equals 2. This parameter will be used later as I describe the numerical results. On this slide, you can see the numerical results. First, I will define several terms used for the evaluation. A user is defined as satisfied if summary frame loss ratio, or FLR, does not exceed 1%. Network capacity is sufficient if the 5G system manages to satisfy more than 90% of users. Let me begin with the single G0Bs, as they are the solutions which do not use the multi-connectivity features. A single FR1 G0B manages to satisfy only 3 users, after which the ratio of satisfied users drops dramatically. This can be explained if we take a look at the FR1 resource usage plot on the right. The drop of network capacity occurs when FR1 usage exceeds 50%. Now I remind you about the peak to average frame size coefficient of 2. Some video frames are twice as large as the average frame. So in the event of packet burst, there occurs packet loss because there is no available resources to serve this packet burst. So the operator needs to take this burstiness into account when managing channel resources. Let me move on to the single FR2 G0B. It provides sufficient network capacity for only 2 users, after which ratio of satisfied users drops. This is because user's position inside of the cell defines whether the user will be receiving continuous transmission. If it's located too far, which may happen randomly in this scenario, throughput starts fluctuating and video frames are not delivered fully. Now on to the multi-connectivity algorithms. Link switching, the green line, link switching uses the estimated throughput metric. It does not provide any increase in ratio of satisfied users compared to just a single FR2 G node B, because the throughputs of FR1 and FR2 channels are so different that the FR1 channel is picked very rarely. As we can see from the plot on the right, the FR1 resource usage is almost zero. Packet splitting shows network capacity similar to single FR2 G node B's option, because again, in the event of the FR2 channel being unavailable, a large portion of the video frame gets lost. And we also see that the FR1 resource usage is substantially higher than for link switching. Therefore, there is no advantage to use packet splitting in this scenario. Finally, we will consider the DBTB algorithm. The maximum number of users with sufficient network capacity equals 14, which is at least twice as much as for other algorithms. Moreover, the FR1 resource usage does not exceed 10%, which allows the remaining 90% of the resources to be used by other user equipment. In this final section, I will make conclusions. Cloud AR/VR is denoted as a killer application of 5G systems because of its strict quality of service requirements. To successfully transmit the traffic of this application, FR2 channels can be used along with the multi-connectivity feature. We developed the DBTB algorithm, which aims to meet strict QoS requirements of the cloud AR/VR traffic and minimize FR1 resource consumption. We analyzed the numerical results of performance evaluation of the considered algorithms and discovered that the DBTB algorithm doubles network capacity for cloud AR/VR traffic in comparison with the state-of-the-art algorithms. Moreover, this algorithm ensures low FR1 resource consumption, which is helpful for providing other users more resources. Thank you for your attention. Now I'm glad to read and answer your questions.
Thank you for your presentation. Okay, maybe one question from my side. Do you consider that all of the VR flows you are transmitting have the same quality of service requirements and the same average bandwidth?
Well, the delay budget associated with the frame or the packet of this frame is defined by its QoS, like flow. And as we can set the delay budget individually for each packet inside of the DBTB queue, we can support both variable frame rates inside of a single VR flow. And as I mentioned, for each data flow, there is a separate queue. So for each queue, there is an individual delay budget.
But do you have the results that can prove that your algorithm you proposed can be applied in the case, for example, when there are several VR flows, but they have different bit rates because, for example, different users have different VR headsets with different resolution or different frame per seconds, or this is out of scope of current?
Sadly, I do not have such numerical results, as I assume that every user requests for the same type of AR/VR traffic. But such an improvement of this work is planned to be done later.
Do you need some improvements of the algorithm, or the current version of the algorithm can be applied?
I don't think so. I think it already supports both different types of rather different parameters of the AR/VR traffic and variable frame rate of a VR flow. So the problem is to notify the PDCP protocol about the QoS requirements for each flow.
Okay, thanks.
I will read the question by Evgeny Korneev. Thanks for the presentation. I might have missed related notes in your presentation, but have you considered traffic with constant bitrate only, or your algo was studied with variable bitrate as well? I did only consider constant bitrate only in this scenario, but again, I am confident that the DBTB algorithm will also support variable frame rate, because it is possible to define delay budget for individual packets of the queue. Yeah, thanks for your question, Evgeny.
May I ask a question?
Yes.
So in your scenario, you consider the case of two channels. Can the proposed scheme can be extended to the case of multiple channels? So, for example, we have several mmWave GNBs in the vicinity and one FR1 GNB. So, yeah.
Surely, this is one of the direction for future work. When I defined multi-connectivity right here, I didn't say specifically that this is defined for two base stations only. There is one mmGNB, like FR1 GNB, but there may be multiple sGNBs, which will cover the area independently. So yes, I have plans to extend the work to the case of multi-connectivity with multiple base stations, not only two.
Okay, thank you.
We have one more question in chat.
Oh, yes. Dmitry Bankov, thank you for the presentation. As I understand, the plotted results were obtained with 100 experiment runs. How big is the variance of the obtained results? Good question. We have measured the variance, but I cannot show it right now, but we have determined that the variance is not more than 1%, and therefore 100 simulation runs is enough to validate the numerical results, to use them. Yeah, thank you for your question, Dimitri.
So I guess that's all for today. Let us thank Maxim for his interesting talk. Also, I want to thank all participants of the seminar for joining our seminar and asking questions. See you. Goodbye.
Thank you for your attention again, for your questions. I'm glad to participate.